Hey everybody, this is a basic lecture on oscillations for pre-IB physics. So an oscillation is just a vibration that repeats itself. It's one form of periodic motion, which by definition is motion that repeats itself at regular periods. So hopefully you're already familiar with period and frequency, but of course they come up a lot in periodic motion. Now the difference between oscillations and circular motion is that oscillations are back and forth, while circular motion involves going in a circle. And we can use a lot of the same ideas to analyze periodic motion and circular motion, but they are going to be slightly different. Here in this image we can see a simple pendulum undergoing an oscillation, periodic motion, and underneath the pendulum is actually a graph of the displacement against time, displacement from equilibrium. And anytime we have a specific type of periodic motion, we'll always get that curve. It's called a sine curve or a cosine curve. And yes, it is the same as the trig functions. They give us that curve if we graph them for different angles. So oscillations are vibrations that repeat themselves. They can be driven externally by some external force. In this example, our pendulum is repeatedly pulled back down by gravity, and so it oscillates. Or they can be driven internally, like a mass on a spring. The spring is what's pulling it back to the center. In all cases, our velocity is 0 at the extremes, and our velocity is going to be a maximum when we are at the center. A couple of examples of oscillations. Anytime you're really listening to any music, that sound is produced by an oscillation of something, which causes a wave of the same frequency to vibrate through the air. So tuning forks or guitar strings are all examples of oscillations. But let's define a few terms related to oscillations. Some of them you may already know. Number one is amplitude. Amplitude is the maximum displacement from equilibrium. So in this case, our amplitude is that distance from the center to the maximum, or the center to the minimum. You can see that those distances are going to be the same. The point of zero displacement is the equilibrium position. We always measure our displacement x from equilibrium. One other note, amplitude is sometimes written as the variable capital A instead of x naught, but you might see x naught, you might see A for amplitude. We would say x is the position at any given time, and x naught is the maximum position, or amplitude. The period, which you should already be familiar with, is the time it takes for the mass to complete one full cycle. That's the time it takes to go from one point to a similar point in motion. We could start measuring the period from either end, or we could actually start at the middle. If we measure from the equilibrium point going left, we just have to go through that full cycle to equilibrium going left. And no matter where we start measuring the period, we should always get the same value. Frequency is how often, or the rate at which cyclic or periodic motion repeats. It's measured in hertz, which is the same as cycles per second. How many times an oscillation or repetition occurs each second. And it's the inverse of period. So frequency is 1 over the period. If you know period, you can get frequency. If you know frequency, you can get period. In this example, in the previous example, the period was 24 seconds, so the frequency would just be 1 over 24 seconds. If we plug that into a calculator, we get 0.042 hertz. Hertz is the same as 1 per second. So let's look at this example. We'll pull this mass to the right and begin its motion, or we could push it to the left and release it. So we have the same system, but started from different positions along the motion. Starting stretch versus starting compressed. Both systems are going to have the same values for period and frequency because they're the same system, and the period is just defined based on the mass and the spring constant, as you know. But the fact that they're along different parts of their motion means they have a phase difference of half a cycle. So phase or phase difference tells us about how offset two motions are for two things of the same frequency. We would have to skip one of these ahead or behind by half a cycle for them to be in sync. So here's another example. We have two springs. One started fully stretched and then we release. And one started unstretched with a push to the left. What's the phase difference going to be between these two? Well, if we think about where they are in the motion, our phase difference is going to be 1/4 of a cycle. Because to get them synced up, this top one has to go an additional 1/4 of its cycle. Full cycle would be towards the middle, towards the left side, back towards the middle, back towards the right. So just going toward the middle is 1/4 of a cycle. Here's another example. Here we have stretched and released, and then unstretched with a rightward push. What's the phase difference going to be? Well, we can just see how much we would have to shift the first one to get in sync. And it's going to be 3/4 of a cycle. We've got to go to equilibrium, to the leftmost, the most compressed point, then back to equilibrium, moving right. So, so here's an example of a spring oscillating back and forth, we can see. And we want to just show that the acceleration of a mass spring system is related to the displacement by this proportion. Acceleration is proportional to negative displacement. But we can always get that just from Hooke's law. So Hooke's law says the spring force is equal to negative k times x. But force is just mass times acceleration. There's no other forces acting in the horizontal direction. So ma equals negative kx. Remember, these are vectors, acceleration and displacement. So a is equal to negative k over m times x. K and m are both constants, so the acceleration then is proportional to negative displacement. And in fact, this is going to be true for a lot of different types of motion. Whenever we have this criteria where acceleration is proportional to negative x, it's called simple harmonic motion, and it's an incredibly important type of motion, and it shows up all the time in nature. Because we get a lot of situations where our acceleration is proportional to negative displacement. We already showed that a mass on a spring executes simple harmonic motion because we already showed that the acceleration is proportional to negative x. Whenever we have that, then we are undergoing simple harmonic motion. Keep in mind that negative sign just tells us the direction of the acceleration is opposite the displacement. We can see that here. If we displace our spring to the right, our force is to the left, so our acceleration is to the left. If we displace our spring to the left, the force is going to be to the right. So anytime we have a restoring force of this form, we always get simple harmonic motion. If we graph simple harmonic motion, as we showed before, we get this oscillation, this back and forth curve. Our y value is displacement and our x value is time. And this is actually going to be a perfect sine curve or a cosine curve. So that's how we get this kind of back and forth curve. It's just sine or cosine. we have a graph, we can always easily get the period by just looking for the time between repeated cycles, from the most negative point to the most negative point, or we could do from equilibrium going down to the next equilibrium going down. We could do most positive to the most positive point. No matter where we measure it, we should get the same value for the period. Qualitatively, we can also think about energy in simple harmonic motion. So here's a pendulum, and a pendulum does undergo simple harmonic motion as long as it's only a small angle vibration, which this is exaggerated. And this graph shows us the transformation of energy in our pendulum. Oops. The size of the red bar represents the kinetic energy, and the size of the green bar represents potential energy. In all cases, we're going to oscillate between kinetic and potential energy like that. If friction and drag are both zero and there's no external forces, then our total energy is going to be constant, just like any other scenario. And we could actually graph the kinetic energy and the potential energy on the same graph, on the same curve, the same axis. Let's see what our graph shows. And we can see that they also oscillate with that sine-like curve. It's actually not a sine curve, it's actually a sine squared curve, but that's not that important right now. You can also see that if we were to add these two together, they're always going to add to the same value, and that value is going to be the value in the middle, the center point of that energy. Okay, here's an example of simple harmonic motion. We want to find the amplitude of our motion. Remember, amplitude is the maximum displacement from equilibrium. So we can see our equilibrium point is right at 0. X equals 0 millimeters. And so we just need to find the displacement from x to the maximum. So that's going to be our amplitude, either x naught or maybe a. Pretty easy to get from that graph. Next, let's sketch this graph for the situation where the amplitude is cut in half. Now we know from the previous lecture that the period isn't affected by the amplitude, how much you displace your simple harmonic oscillator. So it's just going to have the same period and frequency, but it's going to get to half the maximum height. So since the amplitude was 2 millimeters, our new amplitude is just 1 millimeter. Whenever it was at 0, it's still at 0. Whenever it's at -2, now it's at -1. Last of all, actually this is slightly off. This isn't actually a quarter cycle out of phase. We drew a blue graph here, and we want to determine the phase difference between it and our original graph. You know that one cycle is going to be from the start to a similar point, so equilibrium up to equilibrium up. So to find the phase difference, we need to figure out how far maybe this maximum is to this maximum relative to the cycles. And it looks like, well, this is one cycle, and from here to here is a quarter cycle, and this is, how far does it go? 1, 2, 3, 4, 5. So actually I think this is supposed to be a quarter cycle out of phase, but the graph is just slightly off. But we can see that it's slightly less than a quarter cycle out of phase. If we wanted, we could calculate that. So here are the three equations that you're going to have to deal with for simple harmonic motion. Period is one over frequency, of course. If you know one, you know the other. The period of a mass spring system is 2 pi root m over k. Be careful when you're solving this for m or k. If you square both sides, then you're going to get t squared equals 2 squared pi squared times, well, the square will cancel with the square root and you just get m over k. But make sure you square all of your terms if you're squaring both sides, including that 2. Same thing with the pendulum. Pendulum period is 2 pi root L over g. And so if you need the frequency, you can always just calculate the period first and then take the reciprocal. So in summary, simple harmonic motion involves a restoring force proportional to the displacement from equilibrium, but in the opposite direction. A graph of this motion is a sine or cosine curve. We talked about a few properties of simple harmonic motion. Period is the time for one cycle. Frequency is the rate that cycles repeat. And amplitude is the maximum distance from equilibrium maximum distance from equilibrium. Keep in mind that the amplitude is also going to be half the distance from maximum to minimum. So if you only know the range that an object oscillates, that's going to be twice the amplitude. This is going to be our normal amplitude, x naught or a. And two simple examples of simple harmonic motion are a mass on a spring and a pendulum that's displaced at a pretty small angle. Your independent work is going to be the quest on oscillatory motion. It's mostly just period, frequency, and amplitude calculations. But be careful when solving, especially those period and frequency of a pendulum or spring. There's no flipped assignment other than an extra credit video on synchronization of oscillators. And we're going to do a test next class on gravitation, circular motion, and oscillations. That's all.